Pulleys 4. This video covers a fourth example problem relating to a pulley. It's just set up slightly differently to the other questions, but as per usual, the 4 steps apply to the problem. So step 1 is to draw out the situation. A light and extensible string passes over a smooth fixed pulley. To one end of the string, a mass of 800 grams is attached, and to the other an unknown mass is attached. Both masses hang vertically. Okay, so that's step 1. We can complete step 2 and put the forces on. 800 grams is 0.8 kilograms, so the weight is 0.8 g. The tension T acts upwards on both masses. The other one is unknown, so we will say that its mass is m, so mg. So that's step 2. Step 3 is to add the acceleration to the picture. We'll read on. The system is released from rest, and after 1.4 seconds the unknown mass has moved up by 1.5 meters. So this is the one that's going to move up. So the acceleration arrows must be this way around, up on the right and down on the left. Step 4 is to apply F equals ma to each object. So to the 800 gram mass, resolving with down as positive, 0.8 g minus t equals 0.8a. Again applying F equals ma. But to the other mass, so to the weight mg, taking up to be positive because it accelerates up, t minus mg equals ma. The first thing to identify here is that we have 1, 2, 3 unknowns in 2 equations. With the current amount of information, we cannot solve these equations. If you've got 2 equations, you can deal with 2 unknowns. So we've got to get information from somewhere else. Well, in the main part of the question, we're also told about a time and a distance. So it's likely that SUVat will give us some additional information. So lay SUVat out. The system is released from rest, so u is 0. Final velocity we don't know and aren't asked about. A would be helpful. It would reduce one of the unknowns in the 2 equations here and here. The time, we are told, after 1.4 seconds, and the distance covered in that time is 1.5. We're applying this to the lighter mass, mg, and we're taking up to be positive. If we don't know v and don't want it, we want an equation that doesn't have v, so we use s equals ut plus half at squared. Because u is 0, we don't need to write ut, and half a t squared, 1.4 squared. 3 over 1.4 squared is a. A is equal to 1.531. 1.53 meters per second squared. Now we can go back to these equations here, and there will only be 2 unknowns. In fact, in the first equation there'll only be 1 unknown, making it much easier to solve. Just so with a known, 0.8 g minus 0.8 a is equal to t. So 0.8 bracket 9.8 minus 1.53 is equal to t, and that makes t 6.616. So the tension is 6.6 newtons. The question asks for the unknown mass. Well, that's the third and final unknown in these 2 equations here, specifically in that equation. So T is equal to mg plus ma. T is equal to mg plus a. So work back up here, m must be equal to t over g plus a. 0.5839. It'd be sensible to quote this in grams, as the known mass was quoted in grams. So that's 584 grams. Okay. Then calculate the distance travelled by the unknown mass after 2.5 seconds. So we can take the SUVat information and it's asking how far something has travelled. The distance travelled, so question mark next to the distance. The system is still released from rest. We don't know the final velocity. We do know the acceleration to be 1.53. So we would like to use the equation that doesn't have v again. That's s equals ut plus half at squared. Ut doesn't need to be written as it's 0. 1/2 multiplied by 1.53 by 2.5 squared. It's 4.783 meters. So it travels a distance of 4.78 meters in the first 2.5 seconds. As it's distance, the direction doesn't really matter.